This is a starter on Unit 18 on normal modes. What I'm hoping to model is the motion of this system of two onions on two strings tied up there. I'm going to look at a general motion where I'll release it from some arbitrary position, and we want to model the motion of those two onions. Normally with oscillations you're used to what sort of motion? Simple harmonic. I mean, is that simple harmonic? No, it's definitely not simple harmonic. So what we want to try and do is to build up to model that sort of motion. So seeing as you've been a very talented, committed, hard-working, conscientious, brilliant, intelligent, articulate group of students this week, I went into the Bridge of Allen and spoke to the greengrocer who gave me these onions, and I was a little disappointed that she didn't give me anything more exciting to use, because really I think she said to me that she didn't actually have any spring onions for you to use. But never mind. So we're going to be looking at this system, and it seems to be related to what you're already familiar with, maybe a simple pendulum. And just to remind you of the main results for a simple pendulum, imagine a mass on the end of a string at some position making an angle theta with the vertical, and an x coordinate horizontally measured from the equilibrium position. The equation of motion, when we model that, what forces are on the mass?
Gravity.
Sorry? Weight. Thank you. Weight and the tension in the string. When you set up the equation of motion, you get this equation, x double dot plus g over Lx equals naught. And that's the equation for simple harmonic motion, the equation of motion that describes simple harmonic motion. X double dot plus omega squared x equals naught. And that's true if the angle, if the motion is close to the equilibrium position. In other words, as long as theta is small. Simple harmonic motion is that common that you can quote the solutions from the handbook. You don't have to start solving the differential equation. And there are two forms of the solution. Either x equals a cos omega t, where omega in this case is root g over L, plus phi, or this second sort of double form of the solution. There are two arbitrary constants in either, b and c in this one, and a and phi in this one, and they're determined by the initial conditions. But essentially, the mechanics tells us that we've got sinusoidal motion. Okay? So that's the motion of a simple pendulum. So let's look at the data for this problem. So Mrs. Macpherson, the Bridge of Allen greengrocer, sold me two onions at 0.4 kilograms and 0.225 kilograms. I've connected them this morning by two pieces of string, 1.53 meters. Not sure why I chose 1.53, but Mrs. Macpherson assured me that the numbers would work. So I've set up a coordinate system in which the two onions are at some general position in their motion, where the top onion makes an angle theta with the vertical, and the bottom onion is not necessarily on the extended line. It'll make some general angle phi with the vertical. I've taken an origin at the point of suspension with a unit vector I along the x-axis horizontally and the y-axis vertically. Okay. Normally I'd ask you to put the forces in, but seeing as it's Thursday, I think you've probably done a lot of that this week. So what we want to do is look at the forces on each of the onions, and we consider them both separately. And if we think about this bottom one, then as far as that onion is concerned, it feels its weight and it feels a tension from the string. It doesn't know anything about what's going on up here. As far as that onion's concerned, the only two forces on it are the tension and the weight. Call that T3 and 0.225 GJ, the mass of the onion times G. On this onion up here, it's connected to two strings. I've got the word spring in my mind now after this. Two strings, T1 and T2, and the weight of the onion, 0.4 G, and that's acting in the J direction. So again, the goal of mechanics is to take F equals ma, model the forces, we know the masses, the unknown is the acceleration. That sets up a differential equation of motion, the solution of which tells us the velocity and the position at any time t. So before we do that, we need some expressions for the forces. So let's consider the tension T1. T1 is a vector. Its magnitude I'll write as modulus of T1. There are ways in the unit to deal with finding the components of a vector. And just to simplify things slightly, I've actually taken out T1 here. And because that angle is theta, this angle will be theta. So the pull in the string here has got a horizontal component pulling to the left and a vertical component pulling upwards. And essentially we want to replace this tension by two equivalent forces acting in those directions, the two component forces. So in terms of the length of the arrow or the size of the vector, this one is the magnitude of T1 multiplied by the cosine of the angle theta. And similarly this one, the length of that arrow is the length of that side, and that's T1 sine theta. So as a vector, the vector force, the vector T1 is minus T1 sine theta, because T1 sine theta is in the minus I direction, and T1 cos theta acting upwards, which is in the opposite direction to my chosen y-axis, so that's minus T1 cos theta. Similarly for the force T2, T2 is acting in this direction here, and this makes an angle phi with the vertical, so the two components, the projections of T1 on each of these directions, is essentially T1 dotted with the unit vectors in that direction, which involves the cosine of this angle, so we get T1 cos phi and T1 sine phi. These two components are in the direction of the chosen axes, and so the vector T2 is T2 sine phi I plus T2 cos phi j. Agreed? Finally, T3. T3 is a force in this direction here, so resolving into its components makes an angle phi with the vertical, so we have T3 cos phi and T3 sine phi. So these are the vector expressions for the three tension forces. So what we're going to look at is, just like the simple pendulum, we're going to simplify this motion to a certain extent by looking at motion which is close to the equilibrium. I mean, when I had these onions raised, I mean, I'm not going to get on a ladder and release them from that blackboard. So just to minimize effort, I'm just going to look at motion close to the vertical. So the angles theta and phi are small. And therefore, if the angles theta and phi are small, not much is happening vertically. I mean, let's just look at one onion. If I just swing one onion, the distance it's moving vertically is negligible pretty well, isn't it? Yes? Yes. So for small disturbances from the equilibrium, the motion is almost purely in the horizontal direction. So in other words, y double dot is equal to 0. There's no acceleration in the vertical direction. So let's now use Newton's second law for the 0.225 kilogram mass. The total force on the mass is T3 plus its weight, and that must equal the mass times the acceleration. The acceleration vector is xb double dot I plus yb double dot j. That's essentially the acceleration in the x direction, the acceleration in the y direction. And so if we put in the expression over there for T3, this gives me minus T3 sine phi I and minus T3 cos phi j. That's the expression for T3, plus 0.225 gj, and that gives me the right-hand side. And so we can equate the components in the I direction and the j direction, and that then gives me, for the I component, 0.225 xb double dot, and over here it's minus T3 sine phi. So that's what's going on horizontally. Vertically, what's happening here? Well, we've got two j terms here, and we've got a yb double dot. That's the vertical component of the acceleration of the bottom onion. And if we make the assumption that that's 0, we've effectively got statics in the vertical direction. So then if that's 0, we've got T3 cos phi plus 0.225 g is equal to 0. So therefore T3 cos phi equals 0.225 g. Still with us? Yeah. Yes? Right. So we're halfway through the mechanics. But the mechanics will end soon in these problems. Lots of mechanics problems, there's a minimal amount of mechanics, and it's just messy algebra. So let's consider now the other mass and do the same. For the onion up here, the 0.4 kilogram onion, there are three forces, T1 plus T2 plus the weight, and that equals the mass times the acceleration again. If we now insert the expressions for T1 and T2 from a couple of slides, T1 we found was T1 sine theta, magnitude of T1 sine theta I minus magnitude of T1 cos theta j. T2 is this expression here, modulus of T2 sine phi I plus modulus T2 cos phi j. That's just pulling in the expressions for the two tensions from the previous slide. So again, if we do the same here, we can equate the components of I on both sides of the equation. So the I component, 0.4 xa double dot, equals T2 sine phi and then a minus T1 sine theta. So that's the I components. And the j components, minus T1 cos theta plus T2 cos phi equals 0.04 ya double dot. And again, assuming ya double dot is 0, that gives me that the j terms must balance. So that plus that equals 0, which leads me to the equation T1 cos theta plus T2 cos phi plus 0.04 g. So all I've done on these two slides is to effectively get the equations of motion for both masses, both onions, in the vertical and the horizontal directions. So let's pull those together. There are the four equations that we've got from the analysis up to now. And let's simplify these a little bit, because we're examining motion close to the equilibrium position. If the angles theta and phi are small, then for small angles, cos theta and cos phi are approximately equal to 1. The other thing we can put in is, looking over here, this tension T2, these tensions T2 and T3 are equal. There's no pulley that the string is running over. There's no introduction of friction, so the tension is constant throughout. And so we can put the magnitude of T2 equal to the magnitude of T3. Get rid of the sines and the cosines in here. Cosines we can put in as 1. The sine terms, if you look at this diagram, sine of theta is XA over the length of the top string, just from that right angle triangle. So that gives me sine theta is XA over 1.53. Sine of phi, the bottom triangle here, sine phi is this distance over the length of this string. So that's the whole distance, which is XB, minus XA, divided by that length. So we can now introduce those into the problem. And so we can replace the sine phi in the top equation by XB minus XA over 1.53. Cos phi is 1. Sine phi, again, sine theta is XA over 1.53. And these two cosines are 1. So we've simplified the equation, the equations considerably there. And that's, again, that's the mechanics over with. These equations will determine the motion of the system. If we take a look at these, if we look at the second and the fourth equation, out of this equation we get the value of the size of the tension T2. T2 is just 0.225 G. And if I put that into here, if T2 is 0.225 G, add that to 0.4 G, and we get the value for T1 as 0.625 G. So in fact, two of the unknowns have been determined. So if we look at those equations now, we've used equations 2 and 4 here. They've given us the two values for the magnitude of T1 and the magnitude of T2. I can now put these two magnitudes into equations 1 and 3. Okay, if I put T2 and T1 into equations 1 and 3, then I can eliminate the tensions from the problem. If I do that and evaluate the numbers, then equation 1 with T2 in gives me XB double dot equals so many XB and so many XA. And when you put those numbers in, you get that second equation. This equation here, putting the T2 and T1 in, will contain terms in XB and XA again. So when you do the sums in this, you end up with the first equation, minus 13.6 XA plus 3.6 XB. These are very special onions, actually, because these tension T, the T here, or the T's that have gone out now, these are very special onions. They don't make you cry because you can eliminate the T's from the problem. But, okay, should we forget all that? Right. So, what have we got now? We've got a pair of simultaneous differential equations for the motion of the middle onion and the bottom onion. If we can solve these now, we'll get the position XA of the top onion and the position XB of the bottom onion as a function of time. So, in matrix form, we can write the unknown vector as XA, XB, and the matrix of coefficients as H. And what we're going to do is to say, well, in some sense, you can imagine that these onions may behave as a simple pendulum. We saw a rather haphazard motion earlier, but you can conceive of a situation where they may just behave as a simple pendulum. So what we'll do is we'll look for some special solutions, some simple pendulum solutions, some sinusoidal solutions, some simple harmonic solutions. XA is A1 cos omega t plus phi 1, a general sinusoidal motion, and XB is A2 cos omega t plus phi 2. And again, if we're looking for something a bit like a simple pendulum, we're looking for the onions to move maybe with the same angular frequency, the same period. So the key thing here is I'm looking for solutions of this form with the same omega. They may have different A's and phi's, but the key thing here is we're looking for two simple harmonic solutions with the same omega. And for these particular solutions, as we saw earlier, they obey the simple harmonic motion equation. X double dot is minus omega squared x. And in the vector form, the same thing goes through. So we get the vector x double dot is minus omega squared x. And the reason for that, just to remind you, if you differentiate this once, you bring out an omega, cos goes to minus sine. Differentiate again, sine goes to cos, bring another omega out, and a cos omega t plus phi is just x. So that's the standard simple harmonic motion equation. So we've suggested some trial solutions. What we'll do now is to throw these into the equations and let the maths decide whether it accepts those solutions, whether it doesn't, or whether it says, well, maybe, under certain conditions. So if I put those into the equations here, we get x double dot is minus omega squared x equals hx. And what sort of problem does that remind you of? Eigenvectors, eigenvalues. Remember the eigenvalue problem? AV is lambda v. Well, this is like hx equals lambda x. So in fact, what this is saying is that the maths will accept these solutions as long as omega is chosen and is related to the eigenvalues of the matrix H. So if we find the eigenvalues of the matrix H and then change the sign and take the root, then we'll end up with omega values. So let's go through the calculation. The matrix H in our case was the minus 13.6, 3.6, 6.4, and minus 6.4. To find the eigenvalues, which you've been doing all week now, you're finding these in your sleep. Determinant of A minus lambda I. So in our case, we want to look at determinants of H plus omega squared I, because we decided on the previous slide that the eigenvalues are minus omega squared. So we want to look at this matrix here and calculate its determinant, which is the product of these two elements minus the product of those two elements. If we multiply out, we end up with these brackets giving 4 terms. So it's an omega to the 4th equation. And Mrs. Macpherson was absolutely spot on when she said if you use these particular onions, the numbers will work out. Because if you gather those terms together, the omega squared term, minus 6.4 and 13.6, just so happens to equal 20. And 13.6 lots of 6.4 minus 3.6 lots of 6.4 is 10 lots of 6.4, which gives you 64. Very clever, isn't she, Mrs. Macpherson? So this is a quadratic now in omega squared. It factorizes as 16 and 4. And that gives me values for omega squared as 4 and 16. And omega is a positive, it's an angular frequency. So omega is 2 or 4. And so what we want to do now is the solutions of the equations are the eigenvectors from over here. This is the unknown vector x. The solutions are the eigenvectors. So what we want to do is to find the eigenvectors belonging to each of these eigenvalues in turn. So if we consider omega squared equals 4, we have to solve the homogeneous equations a minus lambda iv equals naught, which in our case is h plus omega squared I times x equals naught. So if we put those in, there's h plus omega squared I is that matrix there. So with omega squared equals 4, I get a minus 9.6 there. And here will give me minus 6.4 plus 4, which is minus 2.4. So I then get a pair of simultaneous equations, and the ratio xa to xb from either of these equations is in the ratio 3.6 to 9.6, which is in the ratio 3/8 to 1. Okay, so the eigenvector in this case is any multiple of the vector 3/8 1. Let's look at the other eigenvector. If you put in omega squared equals 16 in that top matrix, we end up with 2.4 here and 9.6 here. And the eigenvector in this case is in the ratio of 3.6 to 2.4, which is 1.5 to 1. And it's in the ratio, well, when you take this over, this becomes a minus, so it's in the ratio 1 to minus 1.5. So the eigenvector in this second case is equal to any multiple of this vector. So that's just a standard eigenvector calculation. So what we've actually got now are these two special solutions, which are called normal modes of oscillation solutions. So the vector x will be the eigenvector multiplied by a1 cos, and omega we found is 2 in this case, and in this case the omega was 4 to go with this eigenvector. Remember, way back we looked for two special solutions, two sinusoidal solutions. The values for the constants a1, a2 and the two phi's are determined by the initial conditions. So let's look at some simple initial conditions. Conditions where we release the system from rest. So if we put those two conditions in and do the maths, those two conditions will give us the value of two of these constants. Now, without doing the maths, you can see that if the system is released from rest, this must be a pure cosine graph, because for a pure cosine graph, velocity is the gradient of the displacement graph. If that's 0 at time naught, the only sinusoid which has a 0 gradient at t equals naught is the pure cosine graph, not a sine graph or a sort of a phase shifted sinusoid. The cosine graph is the only one. And so that means that the phi's must be 0. So I've put in two conditions to get two of the unknowns already. So there are the two normal mode solutions when the system is released from rest. And to find each normal mode, how do we release we've said we release them from rest, but where do we release them? And at t equals naught, the eigenvector here, cosine is 1, the eigenvector tells us the ratio of the initial positions to release the system from. So in fact, this tells me that in this case there are two normal mode solutions, and I'll find the first one. Let me actually give all the details there. I'll find the first one by releasing in the ratio 3/8 to 1, was xa and this was xb. That will have an omega of 2, and so that will oscillate with both particles, both onions moving in simple harmonic motion with the same angular frequency of 2, or with a period of 2 pi over omega, which gives me a period of pi. And similarly, this other one will have an angular frequency of 4 and will give me a period of half that, of about 1.5 seconds. Okay, so let's test out the system. So I want you to do some timing here. So if you've got watches or stop clocks, this is your part of the experiment, your part of the deal. Right, so what I'm going to do is to measure this off. Let's put this over here. So for the first normal mode, we've got to displace the middle onion to the bottom onion in the ratio of 1 to 3/8. Okay, so oh, I don't think I can write on there, can I? It's going to be a blow. Oh. Not quite. And to time some oscillations. 1, 2, 3, 4. You are timing, aren't you? 5, 6, 7, 8, 9. I'm going to stop now. 10. Answer? 31.88. So what would we have expected? 31.4. So a little bit of, I think it was this naughty onion up here who was spinning around a bit. So the other one we want to release is -1.5 to the left. We've got to release them in opposite directions because of the opposite signs here. So we want to take one of them 1.5 units to one side and the other one 1 unit. So keep your eye on that. Keep watching. Now that's one we mightn't have expected, but the maths has told us that that's another possibility of the two onions moving in simple harmonic motion. Is it sinusoidal motion? Both of them. Yeah, it's not bad. With the same angular frequency. So let's time 10 of these. Hang on. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
The previous one,
15.46. We would have expected 15.7. So again, not a bad model. And as I was saying the other day, you can often make drastic simplifying assumptions in a modelling, but you often get remarkably good results. Right, so let's move on to something a bit more interesting now. The more interesting motion is when we just release it anywhere. And as I released it at the beginning, for those who came in late, if I just say pull this aside here, that's in the ratio roughly 1 to 1, so it's certainly not, shouldn't be a normal mode. So if I release that and you follow that, well, as long as it doesn't hit the bottom, if you follow that onion, I mean, that's certainly not a sinusoid, is it? So what we want to do now is to predict the motion when the system is released from an arbitrary position. And this is the key note in the unit, that we can build up the general motion from a linear combination of these simple normal mode solutions? I can see you're absorbing that now. And that's quite remarkable. Any motion of this system can be built up as a linear combination of the normal mode solutions. So we take a mixture of this normal mode and this normal mode, and the mixture is determined by the value of the constants. And that's very important. Adding two sinusoidal motions together to get this rather messy motion, I mean, that's quite something. Right, well, we'll keep things simple and release the system from rest again, which, as we said before, means that the two phi values are 0. So, two phi values being 0, this is the general motion. We need to determine the constants A1. So, if I actually write this out explicitly for each particle, the top element of the vector was xa, so that's 3/8 A1 cos minus 3 over 2 A2 cos, and similarly the xb is the bottom line. So what we need to do is to put in two initial positions to determine the two constants A1 and A2. So we'll try and model that motion I've just introduced. The motion where we pull the top onion aside and the bottom one comes with it, and then we just release it from that position. So what we want to put in is the fact that at t equals 0, xa equals 1, and at t equals 0, xb is 1. And if we do that, at t equals 0, cos is 1, so this is 3/8 A1, and this is minus 3 over 2 A2, and xa is 1. So we get this connection between A1 and A2. If we do the same with the second one, we get 1 equals A1 plus A2, which, if you solve those two equations simultaneously, we get the values of A1 and A2. And check that, the sums afterwards. A1 comes to 4/3, and A2 comes to minus 1/3. So if you put those in, 4/3 into here, 3/8 times 4/3 is a half, and A2 going in there, 3 over 2 times 1 over 3 is 1 over 2, and the same for xb. So that gives me now the positions of A and B at any time. Now, it's still got sine and cosine, well, it's still got cosine terms in, but if the maths is correct, that should give us this sort of shimmy, this sort of, this non-simple harmonic motion. Just to check Mrs. Macpherson's calculations, you can actually run this through on MathCAD. I've put in a matrix there, it's homogeneous, put the h equal to 0. Initial conditions at t equals 0, the initial positions are 1, and the initial velocities are 0. And then it out pops the solution, so that's 0.5 cos 2t, which is that, 0.5 cos 4t, and the other, in this case, the unknown vector is x and y rather than xa and xb. The same here, 1.33 is the 4/3, and minus 0.33 is the minus 1/3. So you can check that on MathCAD. Okay, so what do these solutions look like? Well, I've plotted these out using MathCAD. Let's look at the one for xa, a half cos 2t plus a half cos 4t. So the red line is a half cos 4t, the blue line is a half cos 2t, and if you add them together, the black line is the sum of the two. So what do you notice about those graphs, or anything that strikes you about the graphs? The black one in particular. What's going to happen to it? Is it periodic? Will it repeat itself? it'll repeat itself because the blue and the red graphs repeat themselves. Because of the higher angular frequency of this one, it repeats itself sort of twice as often as the blue one. So the one with the longest period is the blue curve, so the longest period of the whole thing will be the same as the blue curve, and that's a period of pi. If we look at the other solution, xb, we get this sort of behavior. This second one was 1 1/3 times cos 2t, which is this red curve, starting at 1 1/3. Different scale to get this on. The other thing I've plotted is minus 1/3 cos 4t, which is the blue curve. And when you add them together, you get this black curve, which, again, for the same reason, repeats itself. But if you imagine putting this part of the black curve with that part of the black curve, and put those together, there's quite a time when it's flat. So I've actually drawn out now these graphs to go over a longer period, a longer time. So that's what XA looks like, and it's repeating itself every pi seconds, just over every 3 seconds. And notice it's got this sort of behavior, which we did observe. And the other graph, if we now look at that over more than one period, what's noticeable is these long dwell times. You know, it's a peculiar shape, really. It goes flat, those situations. What's that saying about the behavior of this onion round about that time? It's staying still for that period of time. It's hovering, or it's dwelling. So should we test this out? Do you believe it all? No? Right. Fair enough. So let's move this over. Right. Let's go for this one first. What I'll do, I'll put that up in that direction so that we can try and let the onions follow, well, not in time, but certainly we can judge the positions of it. So what I'll try and do, I'll just bring down one period's worth of graph. Now I'll try and center this on here. Now, this is the moment of truth. This is the graph for XA, which is the top onion. So what this is predicting is that if I pull these two aside, let me take that graph down a bit. If I pull this aside, and the both onions are displaced by 1 unit, and I'm going to release them from rest, this predicts that this onion will follow that curve. And that's time going down, but all we'll see is it should swing out to that position, come back in, not come back into here, and then swing out again, and then finally return here. Anybody taking bets? Anybody willing to put a bet? Either way. Who's got faith? Who hasn't? And you haven't been primed, have you? Right, okay. Was that a pin? Okay, here we go. fluke. Follows it. Pretty close, isn't it? Pretty close. Notice also, I'll let it run for 2 periods. It is periodic, because it'll go through that first, and back, and then again, and back. And just to show it's exactly periodic, when I catch it, notice that one will stop without me catching it. One more time. Let's look at the other one with this sort of dwell time. What I've got to do now is to move this down here. It's more difficult to follow this because I can't get the board out of the way. That's black, so you just have to follow this motion on the green board. If you can't see it, just stand up for a few minutes. What this is predicting is that when I release the onions again, you're going to concentrate on the bottom one. So this should go out to the far extreme. Can you see that bottom loop? It should go out to the far extreme there, which is the same as that. And when it comes back here, you've got this dwell time at roughly the same position, well, at the same position we released it. So it's predicting that this is going to fly out quite a long way and then come back and dwell. And the period should be pi. So I'll let it run so you can see it, and we'll just check the period. See the dwell? Yeah. I mean, obviously it goes out of this motion after a while because of the things we've neglected, like air resistance, and this onion is spinning. Should we just time, what, about 5? I don't think it'll go for 10. Just to check the period of the whole thing. So, you ready? 3, 2, 1, go. 1, 2, 3, 4, stop running. 5. What's that? Right. Is that about right? 5 lots of pi, 15, put something. So again, even though it's sort of fairly haphazard motion, or apparently so, it is periodic. And just to finish, if we look at these 2 things together, if I've put them on the same graph here. I've put XA and XB, and it allows us to sort of maybe see the shape of the 2 of the motion together. There's the initial position where they're both released from one unit. This predicts that XA comes in first while XB is still hanging around, while the bottom onion is still hanging around. So this rushes to the center. It then goes out to the far side, and in the meantime, the bottom onion is coming through the center. It then comes back to the center, the top onion, and the bottom onion swings out quite a long way. And then the whole thing is symmetric about this line, so therefore you just reverse this diagram to get the second part until they both meet again at the end of the period. So you've got to put both onions together now and see if you can identify that motion. See, that top onion's around about the middle when the bottom onion's gone out. Okay. Are you convinced? Yeah. Good, good. Okay. What you should take out of this, I think, is not the onions, but this sort of very important principle that the general motion is a linear combination of the normal mode motions. And that's true in more general systems, just in the same way as a note can be made up of harmonics. engineers do vibration analysis on systems by finding all the normal modes. And by adding those together in an appropriate combination, you can look at the sort of vibration of the whole component. Okay? So that's just about it, but I think if you are passing through Bridge of Allen, you should show some appreciation to Mrs. Macpherson. Okay, thanks very much.